Hello everyone, my name is Faryal Khan and my team members are Muhammad Aqib Khan, Murtaza Faisal Shafi and Sakina Shabir. Our topic for presentation is Arrow's theorem in voting theory. Arrow's impossible theorem, also known as the general possibility theorem or Arrow's theorem named after the economist Kenneth Arrow, is a social choice paradox which illustrates a flawed ranked voting electoral system. It comes with some important consequences for democratic processes like voting. The theorem states that community-wide preferences cannot be deduced by converting an individual's preference from a fair ranked voting electoral system. According to Arrow's theorem, whenever there are more than two options, it is impossible to collect and convert every individual's preference to an entire community's preference while following a set of conditions. These conditions are requirements for a fair voting procedure and will be further discussed in the next slide.
According to Arrow's impossibility theorem, in all cases where preferences are ranked, it is impossible to formulate a social ordering without violating one of the following conditions. First, non-dictatorship, which means that a single voter and the voter's preference cannot represent the whole community. Second, unrestricted domain, which requires all the preferences of every voter to be counted, which conveys a complete ranking of social preferences. The independence of irrelevant alternative condition requires that when individual rankings of irrelevant alternatives of a subset change, the social ranking of the subset should not be impacted. Social ordering condition requires that voters should be able to order their choices in a connected and transitive relation, that is, from better to worse. For Pareto efficiency, the unanimous preferences of individuals must be respected. The order of social preferences must agree with that of individual preferences if every voter strictly prefers one of the alternatives over the other.
The easiest way to understand Arrow's impossibility theorem is through an example. So over here we have four candidates A, B, C and E, and we have 7 voters from E to K. So what's happening here is that each voter is giving a preference basically based on who they want the most to win the election. So 3 is the highest preferred rating, while 0 is the lowest rating. So once each of the candidates receives their rating, we sum up the ratings, and we can see that candidate C has the highest rating. So candidate C is winning this election. Candidate B has the second highest rating. Candidate C has the third highest, and candidate D has the fourth highest. So basically, we can say that candidate C is preferred over candidate B, candidate B is preferred over candidate A, and candidate A is preferred over candidate D. So now since candidate D is already has a very low score, so let's say we kick him out of this election. So once we kick him out, then we're gonna have to change the rating system. So first we had 3, 2, 1 and 0. Now we will have 3, 2, 1. So based on that, we'll just change the zeros in the table to ones, and the ones, and then the other ones to twos based on what row they were in. So now if we sum up the ratings, now we see that candidate A has the highest rating, and then candidate B has the second highest rating, and candidate C has the third highest rating. So we can say that candidate A is preferred over candidate B, and candidate B is preferred over candidate C. So now what has happened here is basically that the entire order has been reversed. So that's what an Arrow's impossibility theorem tells us, that due to due to one, let's say one, so like one candidate dropping out of this race or being kicked out of the race, the entire order of who's winning the race changed. Before we had candidate C win in the race, now we have candidate A win in the race. So this is what Arrow's impossibility theorem tells us. So is it possible to apply the Arrow's impossibility theorem in a ranked voting system with two candidates? Let's see if it's possible with an example. So now the highest rating is 1 while the lowest is 0, and we have candidate A, candidate B with 7 voters from E to K. So now after each voter has given their rating, we can see that candidate A is being preferred over candidate B. So what happens now is that if candidate B is kicked out of the race, then nothing will happen. Candidate A will still be winning. So Arrow's theorem isn't possible to work with two candidates. So Arrow's theorem basically needs at least 3 candidates, only then it can be applied.
So there exist a number of proofs of Arrow's theorem, but I'm going over the one which is pretty simple and elegant. It uses two lemmas that are they are explained in the upcoming slides and how they help us proving the Arrow's theorem. Alright, so first we have field expansion lemma. So it says that if a group is decisive over a particular pair, it will also be decisive over all pairs of social alternatives, or we can say candidates in simple terms. So this is not obvious, and to prove this, we consider number of alternative states for them like x, y, a, and b, and then we have the members of the group G and the rest which are not its part. So now we can also assume that by unrestricted domain we can assume particular individual preferences. Now assuming that everyone in G writes A prefer to X and Y prefer to B, and every member outside the group has also same preferences, then it can also be assumed that in group G are already in agreement in terms of ranking and or ranking of X and Y. Like whatever the ranking is, we can assume that G will be decisive over X and Y. So that is G will decide what the social ranking is for X and Y. And now let's assume that X is preferred to Y and G is socially decisive over X and Y. Now by using Pareto criteria, as Faryal explained, all members here are in agreement that A is preferred over X and Y is preferred over V. So in addition, we know that X is preferred over Y, since we know this because G is decisive. So now using transitivity, we should have A preferred over B, as we know. So members in G are decisive as their individual preferences dictates the social preference. So in that way we have shown that this must be the case at the social level, because the social rankings between A and B is the function of preferences individual group members, and it doesn't matter like what the preferences that relate to the other pairs are. So because of pairwise independence, we are able to show this result, which must hold true throughout. So now group contraction lemma says that if a group is decisive over a particular pair, then so is some smaller group contained in it as well. Now its proof is consider it has a group G which is decisive. Now we can partition it into G1 and G2 such that in G1 X is preferred over Y, X is preferred over Z also, and preferences of Y and Z is anything. And for G2 we have X preferred over Y and Z preferred over Y, and X and Z can be anything. So now we have two cases here. Case 1 is that when X is preferred over Z, then as it comes from G1, so since we can see it easily that G1 contains X preferred over Z, then we can say that G1 is decisive here for the case 1. And in case 2, since Z is preferred over X, here we can see from the Pareto criteria that we have X greater than Y, or X is preferred over Y common in both the groups like G1 and G2. So Z is preferred here over Y using the transitive property here. So which comes from G2, as we can see that G2 contains Z greater than Y, or Z preferred over Y. So G2 is decisive here in the case 2. So in the either case, we have shown that either one of the group is decisive over the other. So this basically what precisely lemma holds. Now, previously we have used some axioms in proving our lemmas, like universal domain, pairwise independence, transitivity, and Pareto criteria. So, given these axioms, we end up with the dictator. So, Pareto criteria is the idea that the society as a whole must be decisive over a particular pair. But as we know that field expansion lemma says that if a group is decisive over a pair, then it is decisive over all the other pairs. So, society at large is hence decisive here. Now, this is where we will apply our group contraction lemma, which implies that elements of G can be successively eliminated so that remaining subsets are still decisive. So we will be repeating this process unless each subgroup is based on one individual, and then by group contraction lemma again, we know that either one of the subgroup, that is individual, is decisive, and that individual will be the dictator. So because we know that the dictator is the one and who is decisive over all the others, so this ends our proof of Arrow's theorem. The references that are used to understand and prove this theorem are as follows. So thank you so much everyone, and if you have any question, you guys may ask.